Welcome to week 3 of chemistry unit 2. See, I'm in my office. It's very exciting. It's about 7 p.m. and it's still about 35 degrees. That's what it feels like anyway. So this week we're going to look at elements, matter, compounds. And we're going to start some organic chemistry and look at hydrocarbons. So again, elements and compounds in their most basic form. Elements are on the periodic table. They exist either as Na, S, O, but they actually very rarely exist in this form. And myself. They only exist as NO2 or Na2, SO. Very rarely do they exist by themselves. So, element is the simplest form of matter. So, all my pens are dying. So, elements are the simplest form of matter. They cannot be broken down any further than what they are. All these pens have died in the heat of the cup. So compounds, another one. Compound, 2 or more elements. So these first 3 weeks, well, the first half of this 3 weeks will get quite complicated. Now, the difficulty is going to ramp up quite a bit. 2 or more elements, chemically combined. In a fixed proportion. So, H2O, not the same as H3O or HO. So that's where this definition of in a fixed proportion is really important. Because although it is just hydrogen and oxygen bound together, when you change the amounts of each, it completely changes from water to acid or hydroxide. So if we look at another example of this, sucrose is CH. C6. Something similar to that. Can't remember that. It's not. If I change this to C7, O5, it would not be sucrose anymore. So, at the most basic definition, elements can be broken down. Elements cannot be broken down. Compounds can. And compounds must have a fixed ratio between whatever. So if we wanted to break down compounds, we have to use physical methods. We have physical and chemical change. Again, a fairly simple concept from junior year sciences, but something we need to read. Physical is same composition. Chemical change, the composition difference. I like to use wood. If I cut a single piece of wood into two, I just have two pieces of wood. It's still wood. I've just changed the physical appearance. If I burn the wood in the presence of oxygen, in a combustion reaction, I will produce carbon dioxide of water. So, what was there originally? Wood and oxygen is not here anymore. I cannot reverse that reaction. Physical, I guess I could glue the pieces of wood back together. Chemical change, you cannot reverse it. You get change of color. So the signs, change of color, this pen is dead as well, excellent. Change of color, smell. I'd like to all this. There we go. You get gas being produced. The black one actually working better than before. You get heat produced. So that's the difference between a physical and a chemical change, a physical and chemical reaction. A good way of doing this, if we took our sucrose, I don't know if anyone's tried to make caramel before, or seen what happens when someone tries to make caramel and they burn it. The sucrose will actually break down. Once you heat it to like 300 degrees, it will break down into pure carbon and water vapor. So you're just left with a black mess and a ruined flame. If we were to look at, again, let's pretend we're making caramel sauce. Now I'm hungry, haven't had dinner yet. So we take sugar, we have water, in sugar. That's a physical change. We can reverse that. We then take this and we heat to 300 degrees Celsius. You'll smell this. Again, we have pure carbon and H2O. So that is not reversible. This part here is reversible. We heat it to 300 degrees, we get a chemical change that is no longer reversible. The number one rule is that the chemical properties of compounds are very different to the chemical properties of what makes something compound. So classic is sodium chloride. Sodium is a group 1 metal. It is explosive. It is deadly. Reacts violently with water. Chlorine, halogen, group 7. Deadly poison they used in World War II. We mix them together. We have sodium chloride, or table salt. So quite different. So quick little. So we have mixtures. And substances. So, if the composition of a material is fixed, it is a substance. So sugar, if the composition varies, for the varied composition, it's a mixture. I'm going to draw an amazing diagram so that you can use it to figure out. So matter is at the top. So we have a substance here. Over here we have our mixture that we have of varied composition. So definite composition here. So it's either an element or a compound. Element, compound. Then a mixture. So homogeneous mixture. On the other side we have mixture. So homogeneous is a uniform solution. So if you were to look at sugar and water, heterogeneous, we're talking about sand. So homogeneous mixture is sugar and water. Heterogeneous mixture would be sand and water. We have two distinct phases here, and there would only be one phase there. So that is all I'm going to do on that. We're now going to go into our organic chemistry or our hydrocarbons. My favorite topic of the month. So, anyone that's watching or in the chat now, think of what a hydrocarbon is, or what we use them for, or anything to do. Any ideas, anyone watching? If you're watching the recording, take 30 seconds to quickly Google or think about it for something. So, very creative. It's a compound that contains carbon, and hydrogen. We use these as our fuel. So, natural gas, so methane, ethane, propane, which is what they use to power your cooking, propane and butane. And they make up this huge, giant, complicated world that we call organic. So, if you're watching at home, watching the recording, have a Google search for why is carbon so important. Everyone, 2 minutes, have a quick search of why carbon is so important. If you're watching the recording, you can either do that or skip forward to it. Carbon is so important because these hydrocarbons are the basis of life. When we're looking for signs of life on other planets, we're looking for hydrocarbons. Carbon is in group 4. So it can create covalent bonds with 4 other elements. So it can create 4 other covalent bonds. The very most basic concept is that carbon creates 4 very strong covalent bonds with hydrogen. This is called methane. Everything that we require for life is based on this line. So when we're looking at fuel, so when we burn methane in the presence of oxygen, each of these 4 bonds is broken. And we get a release of heat. Coal, natural gas are all just basic hydrocarbons. We burn them in the presence of oxygen, it gives us heat, creates steam, and dries out. Now, we want to get more heat, we just add more carbons and hydrogens. We have previously look at it like this. The way that they are named is based on 2 factors. So we have what we call the carbon backbone. We then have, we name it based on the number of carbon atoms. And the type of bonds. So this would look like this. We would draw it out. Fortunately, organic chemistry and hydrocarbons and everything to do with this is built off a very basic set of principles. Now, those basic set of principles are quite complicated, but once you understand them, you should be able to just apply them as it gets more complicated. It gets more complicated with the same basic principles. So we have generally so we use a 1 to 10 naming convention for this. One carbon atom is called link. The second is called heat. third is called 4 years. If you've just done this grade 11 or you're heading to grade 11 or whatever, just remember these. Carry them onto your forehead backwards. After butane, it's all fairly logical. Meth is produce hex hep. This doesn't change. This, if you go and study chemistry, this will haunt you all the way to the end of your degree and beyond. Still haunts me, all me to know. The first naming convention is how many carbon atoms go up. The second is the type. So if we were to look at it, so here, that is a single bond. We have that's a double bond. That's a triple. So that is the bond between the carbon atoms. Now, here we just have single bonds. So if we have single bonds, it's called an alkane. Single bonds, alkane. If we have a double bond, it would be an alkene. If we had triple bonds, be an alkyne. Triple bonds, alkyne. And a good way to remember this, A comes first in the alphabet, E comes second, Y comes third. That's the way I teach all my students. You know, it seems like a lot, but the rest of organic chemistry is based on this, principles. I think I don't teach English much. Okay. So now we know what would this called. I'll give everyone a minute to figure it out. Using this number of carbons as an alkane, alkene, So, how many carbons is here? 3. So, when we're naming them, we call it propane. So we take pro, and then we add amine. What about if I have what if I had this? What would it be called? So Izzy says propene, but she thinks she's wrong. Izzy, you are correct. Presence of double bonds, it's an alkene. 3 carbons is propene. So, and this is a good time to revise what we call octet. So each carbon can only be surrounded by 4 bonds. So if I was to change this to a triple bond, I would have to get rid of it. So what would this be called? Izzy, you are 100% correct. Propane. Propane. Okay. Let's change it up a bit. See if I can't trick you. I'll leave that there because I'm not holding that. But not this time. What are we looking at here? Butane. We're looking at here. Okay. So it really is as simple as that for our basic hydrocarbons. There is one concept I don't think I explained there. Was the idea of what we call saturated hydrogen. So alkanes are saturated. Each carbon atom is completely surrounded by hydrogen. An alkene is an unsaturated hydrocarbon. Unsaturated hydrocarbons are not completely surrounded. Okay. Let's add some side chains into this. Make it a little more difficult. But remember the basic name. I'm going to give everyone 30 seconds to scratch their head and go, what is this spiral? So now we look at the concept of what we call an alkyl site. You're on the right track. Definitely on the right track. So what we want to do is do exactly the same thing as we did before. So we name this guy here. How many carbons are we present? Three carbons. So the parent molecule, the parent chain here is 4. How many carbons here? So meth. And what we do with the alkyl side chain is we add Y. So methyl is this guy here. He is the side chain. But we also need to know which carbon does this guy come on. We count 1, 2, 3. So it will be called 2-methyl. 2-methyl. The most common question I get, which side do we count? Now, it doesn't really matter here because it's the second. You have to count from the side, will give this side chain the lowest number. So if I was to put let's do this one. So what will we call this? So yep, which carbon does it come off? What number? So 2-methyl pentane. So some people make mistakes, they count this, which would give us 4 methyl pentones. But we have to have the closest number. So we have to have the lowest number. 2 methyl pentones. All right, whilst we're here, let's do some crazy stuff. Dun, dun, dun. Now we have 2 such. So what would we do here? So it's still pentones. It's still methyl. We still count left to right because 2 and 4 are the lowest numbers. So 2 and 4 go over. Actually, they shouldn't go there. They should go, yeah, it's a bit close. 2, 4, dimethyl pentane. Di telling us that there is 2 methyl groups attached to a 5-carbon backbone. 1 coming off 2 and 1 coming off 4. For a final spanner in the works. And now added a 2-carbon side. So what's the parent hydrocarbon chain called? How many carbons are there? So look at our little cheat sheet on the left, or the right, or either. So it's still pentane. Because it doesn't matter which way we go, we can look this way. Oh, hang on. There we go. I've added an extra carbon on the top. So there's 2 carbons on this side chain. So we have ethyl and methyl. Which carbons are they coming? So there's still only 1 ethyl. There's 1 methyl, 1 ethyl. Which carbons are they coming? So methyl is coming off carbon 2, ethyl is coming off carbon 3. So we have to put them in alphabetical order. So 3 ethyl, pentyl. This tells us that the longest continuous chain of carbons is 5. That it's coming off the second carbon. We have an ethyl group, a methyl group, and then off the third carbon we have ethyl. Okay, that's about 6 weeks worth of chemistry there. I will see you guys in next week. TV is starting to shut down. Okay, thanks everybody. I'll put the recording up ASAP. That was a lot.